network elements. In the presentation, I will talk about the network OSI model and a little bit about how TCP/IP, which is the protocol of the internet, is reflected in the network OSI model. OSI model says that there are 7 layers of the network: the physical, data link, network, transport, session, presentation, and application layers. And these layers depend on each other. Let's have a look at what these layers really are. The first one is the application layer, which is directly used by the application. On this level, the meaning of the data is important. And it's usually like an API. When we want to send some data, then we use an API on this level that says that this is the data I want to send it. And then the next level is that where we pass the data on, and that's the presentation level, which talks about the formatting or cares about the formatting of the data. It can be JSON, it can be XML, it can be protobuf or some other syntax for the data, textual or binary format. This is about how the data is converted from its meaningful structure into a certain byte stream that we can send over the network, and on the other hand of the network where the application we are communicating with can understand this format and restore the data for the other end of the application over the network. The next layer, where this already converted byte stream, so from the presentation layer, is passed on, is the session layer, which is essentially manages the connection between the communicating partners. So this layer is responsible to make the connection and how the data is transferred. The next layer is the transport layer that ensures that the quality of this connection is good enough. And if it's not good enough, then it does resending of lost packages. And also it acknowledges sent and received data, so the sender knows that what is arrived on the other side. And the next layer is the network layer, which directs the data through the network. So this is the routing, what the routers do. This is the layer that is responsible for finding the way for the data from one endpoint to another endpoint. And the next layer is the data link layer, which is responsible for the connection between the adjacent network nodes. So when we have 2 routers connected to each other over some fiber or over something else, whatever, that's the next layer, that's a physical layer, but we have 2 routers connected, then data link layer is responsible for the transfer of the data between these 2 nodes. Higher layer network then does the routing and sends the data on. But from one router to get the data to another router, or to get the data from an endpoint like a PC or a server to the next router, that's the data link layer. And last but not least, most importantly, the physical layer that defines the electricity level, signal level, like 5 volts or whatever, frequencies of the transfer. So radio frequencies, maybe the amplitude of some light, the number of photons, whatever is needed in a fiber optics, that's the physical layer. Let's have a look at how the TCP networking matches these layers, which are generally a model of the network. If we look at it, then on the left side we see the OSI model, on the right side we see the TCP/IP networking. And if you are familiar a little bit with TCP/IP networking, that you should be, because we were talking about FTP, HTTP, SMTP, and many of these protocols and TCP and IP in this tutorial, then you will understand a little bit about these different layers. So generally, FTP, HTTP, SMTP, and all these protocols are responsible for all the things that the application, the presentation, and the session layer has to do. The transport layer is the TCP protocol itself. Then the network layer is the IP. And since IP wouldn't work without any physical layer that it travels through, so it just doesn't travel through thin air, unless it's radio, of course. But we have a data link and a physical layer. And Ethernet is at the same time, it defines the data link protocol, so it's a collision detecting network. And also it defines the physical level because it defines the radio signals if it's a Wi-Fi, and also defines the signal level and the speed if it's transferred through some cable or twisted cable pair. Let's talk a little bit about the TCP header structure, because TCP is very important when we are sending and receiving data. And then you can see that there is a source address, a destination address, and very important that we have a source port and a destination port. And in this case, these are very important. And then when you are at home and you are using and you are connecting to a server, then this is how it really works. With a TCP connection, these things in the header help us and help the network to transfer the packages. So let's have a look at that. We have a TCP connection, and we have the clients, and we have a server, and we have a connection from a client to the server to the same port, because the server runs a HTTPS service on the port 443, for example. Then all the clients are connecting to the same port on the same server. So when the server answers and sends back a package, then it's very important that it knows where to send it back. And that's the reason why there is a source port and a source address in the TCP header. If there is a client which essentially runs two different connections to the same server, then the source port actually will be two different ports for the two different connections. And if we are running out of ports, then we cannot make more connections from a certain client. And this is very important to understand, that even if somebody is running from the same client, so we have multiple connections from the same client, the server will know when it's sending back the packages to the very same client that one package goes to for one connection, the other one is going for the other connection. So this way, when we are looking at a connection, let's say that we are sending data from the client which has the TCP IP number 192.168.0.1 and the source port, which is usually assigned randomly by the operating system, is 32,654. And then we are targeting the server 83.166.169.231 to the port 80, which is the standard HTTP port. And when the answer comes back, then the source address and the source port and the target address and the target port are actually just swap. So what was the source port becomes the target port, and the other way around. And also for the address, what was the source address will become the target address, and the other way around. Actually, you don't directly connect to that server, you have a home router. And how does it work? You have the router in the middle. And when a client tries to go and connect to a server, then the router will route the connection to the server. But how does it work? Well, the router uses network address translation. And the reason for that is because the example address I was giving, 192.168.0.1, actually is a private address. It should not appear on the internet. And if you look at it, it's very likely that your PC or your notebook has this address or something very similar, 192.168.0 or 1 dot something. And many people all over the world have the same address. How could it be? On the internet, no two nodes should have the same address. Otherwise, when we address somebody with this IP address, then how do we know which one? Addresses, as the name defines, should be different. That's why they are addresses. So what the router does is network address translation. On the left side, on the client, there are so-called private IP addresses. And the client sends out a package and it thinks that it can reach the server, which is on the public internet with that very specific IP number, as you can see on the screen. And then the router gets this package because on the network layer, it travels to the router. And then it says that I cannot send this package unmodified to the server because the source address is a private address. So it replaces the private address with a public address, which is its own public address. So the router is directly connected to the internet, and it has a public address which is reachable from the outside. And then it sends out the package like if it was his own something that he wanted to send this package. And when the answer comes back and the source and the destination ports and addresses are swapped, so the server answers to the router, then the router realizes that this package is an answer to the connection that it was making on behalf of this very specific client, and replaces the target address and the target port and sends it back on the left side on the private network, the home network. Generally, this is network address translation, because somebody may understand it easier with not specific numbers. So we have a client IP and the client port, and the server IP and the server port. And that's on the left side. That's how the package travels from the client to the router. And then the packages from the router to the server travel with the information with the router IP and the router port, and the server IP and the server port. And then the answer, because the server has no knowledge about what's behind the router on the private network, the answer is sending from the server IP server port to the router IP router port. And then the router changes it back and sends the package with the source address server IP server port to the client IP client port. And the client doesn't see that network address translation has actually happened. It feels like with his private address, which is assigned to many clients on different private networks, like if that was on the internet, at least for the connections that it initiates through the router. We also use SSH tunneling, which is very important. And for a developer, it's very important that the SSH can use not only to log into a server where you can have a Unix prompt and you can issue Unix commands, or for that matter, if it's Windows or some other operating system, then other operating system commands, but you can also forward TCP connections between local and remote ports. How does it work? Well, with SSH tunneling, you have the client, you have one server, and you have another server. And let's say that you cannot reach the server 2 from the client directly, but you can reach the server 1 from the client, and you can reach server 2 from the server 1, but not directly from the client to server 2. What can you do in this situation? Well, if you can use SSH, then you can use the command line option -L. And then you can specify an X port, the server address, server 2, and then Y port. And then you can log into server 1 with this SSH command. And this way, the SSH actually will bind itself on the port X on the local host, and will act also on the server 1, that if anything is connecting to the port X on the local host on the client, then any data will travel through this SSH connection to server 1, and on server 1, this connection will be sent to the port Y on server 2. So that way, it looks like if we moved the port Y on server 2 to the port X on localhost. And that way we can access through this channel with any TCP connection from the client, server number 2. For further information, you can also use it backwards, and you can read the documentation of SSH, and it's very important that you understand how to use this.